All right. So on Friday, we were going over benzyne reactions, and we kind of had two kind of types we'd gone over. So one where you have an aromatic halide and a base. And the other method we had for making these was you had like a leading group like a triflate, and then a silicon group. You would add TBAF, and then you could add an external nucleophile. Right. So in both of these, we're going to make a benzyne. And in both cases, we want our benzyne to be symmetrical so we don't get multiple products. So here we set it up that there's only one hydrogen you can remove when making your benzyne, right? So that'll make our benzyne because there's only this one hydrogen here. And then we can add our hydroxide from our base to either side of that benzyne to make our phenol product. Right, and it doesn't matter if you add to the top or the bottom since it's symmetrically the same thing. Right. In the second example, we have a little bit more leeway with our setup, with our starting material, because it doesn't matter how many acidic hydrogens we have. All that matters is we know that we're always going to make our benzyne between the two carbons that have the triflate and the silicon. So here the TBAF makes our benzyne. Right, and it's only going to be between the carbons that have the triflate and silicon. And then we can add our nucleophile, which in this case is ethyl, right? Because we can say this carbon is negatively charged, that bromine is positively charged, not bromine, sorry, that metal is positively charged. And that is going to give us our product. So we got through 3 of the 4 ways to make benzynes. And today we're going to do the last way to make benzynes. So the next way to do it, or to make a benzyne, is you have a carboxylic acid and diazonium salt. So you know what a carboxylic acid is. Then you have N triple bond N with a positive charge. And this is your diazonium salt. Basically, diazonium salt is like N2 gas that is just like tenuously stuck to your molecule. Right? If you break the carbon-nitrogen bond, you end up making N2 gas, which is really stable. Right? And that's kind of the driving force for this reaction. So all you have to do is heat this, and it will decompose into the diazonium salt, into CO2, N2, and you generate H plus during the reaction. The CO2 and the N2 are both gases, so that's what kind of helps drive this reaction. Is you warm it up, and you're making this really unstable thing, this benzyne, which is high in energy, but you're generating CO2 and N2, which are both really stable gases. So you're getting all this energy from making these stable gases that's kind of offsetting the fact that you're going uphill by you're going from something that is stable in the benzoic acid to the unstable benzyne. you're offsetting that energy change by making a bunch of stable gases. This reaction, the mechanism is pretty straightforward. So the electrons in the hydrogen-oxygen bond will come down. That causes you to break this carbon-carbon bond, which is going to generate your CO2. And then that breaks the carbon-nitrogen bond that makes your N2. So that gets you here. So this is your CO2. This is your N2. So again, this is another one where you know where your benzyne is going to end up, right? It's going to end up between the carbon that had your carboxylic acid and your diazonium. So what these get used for is you can use these to do cycle additions. So right, the N2 plus, that's the shorter way to write the diazonium out as opposed to having to write the whole thing. Right? So if you heat this and you have, let's say, a diene, you can think of your benzyne as just a dienophile, where your diene can react with that and do a Diaz-Alder reaction. It's a little backwards from how we did it before, but 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it's basically just doing a Diaz-Alder where your dienophile is an alkyne, but it's a benzyne instead. Right, so we do this, we'll end up making a 3-membered ring, sorry, a 6-membered ring. As such. These are harder to add like nucleophiles to because in the mechanism you make a bunch of acid. So you've got all that acid floating around, so it's not like you can add a Grignard reagent or the methyl magnesium bromides that you saw before because they'll just react with the acid.
The question was, why do the double bonds in the starting material in the product move around so much?
Yes, so remember if you look at, I'm going to slip over for a second, right? So this and these are just resonance structures of each other, right? So, right, you can kind of get a withdrawn little circle, right? So, yeah, I know, like, maybe it would have been better for me to, like, start with, let's redraw the same thing I had, like that. That's where the benzyne's going to be. But it doesn't matter. Like, they kind of get there in the end anyway. Yeah. Yeah, I'm sorry. I'm sorry. Like, I try to think of it, but then sometimes I forget. But yeah, so, like, here did a good job, right? The double bonds are, everything's kind of stays where they are. But yeah, it doesn't matter. So I've kind of introduced diazonium salts, and I want to uh, kind of show you other ways to make them, and then other ways to use them. So diazonium salts come from anilines. So to make a diazonium, you need to have an aniline. And then there are kind of two ways to do this. Treat it with sodium nitrite, and then strong acid like sulfuric acid. This acid can kind of swap. It could be HCl, HBr, etc. Just any strong acid there. And you will turn your aniline into a diazonium salt. I also sometimes will see, do this in the early class, you can write this as NaONO. So 6 of one, half dozen the other. They're effectively the same thing. This I went and checked. This is the more right way to do it. So you can do it there. We use like a totally inorganic reagent, or you can add a carbon chain to your nitrate. So you can have your aniline, and then you have a carbon chain on your, again, stuff like HCl, HBr, etc. We'll do this. And we'll make your diazonium salt. The reason you'd have the R group, the carbon chain on it, is if for whatever reason there's a solubility issue and you need that a more organic soluble reagent. So the most common one is isoamyl nitrate, where you just have this 5 carbon chain coming off the oxygen. It's kind of the most common reagent for this. So these reactions work really well. You can just take your aniline, add your reagent, and you're going to make a diazonium. What is nice is it only matters where your aniline nitrogen is at the beginning, right? It doesn't matter. Doesn't matter any of the directing groups or anything. As long as the functionality is fine with being around a strong acid, you're just going to turn that NH2 into an N2 plus. Now these reactions are, like I said, they're really, really easy. Usually you just dissolve your stuff in ethanol, you add in your nitrite, you add in your acid, and you get these really pretty, brightly colored crystals that just crash out of solution and you can filter it off. But there is kind of a problem. So if you ever watched the 80s classic Gremlins, right, there's a ton of rules that you have to follow or the gremlins go crazy and they turn scary.
Never, never feed him after midnight. You got it?
4 or 5-year-old me didn't know this and had my grandpa take me to the movie. And like 20 minutes in, I was like, we out. Gots to go. This got scary. I was like, little furry guys, I was in. Scary guys, I'm out. Right, so like I distinctly remember being like, nope, we gotta go. We gotta go. Um, Diazonium salts are similar. Uh, if you dry them out, they explode. So you have these nice crystals that you isolate, like via filtration. When you vacuum filter them, you have to leave them wet because if you dry them out too much, they get exploding. Um, if there's metal around, they explode. So you know how all the spatulas and stuff that you use in organic lab are metal? Nope, we got to use plastic ones because the metal in the spatula can catalyze the decomposition of the diazotic salt. So basically, it can catalyze the nitrogen gas coming off of the diazonium or coming off the molecule and making a bunch of gas really quickly is how things explode. So you can't use metal spatulas. Right? I used to make a bunch of these and like I'd get like a blast shield out, much not too dissimilar to this. A blast shield out, and I was like, I can't get blown up. If I lose a finger, I'll be single forever. Like I'm barely dateable relationship material as it is. Missing two fingers, just like get 8 cats and live alone. Like just done. Right. So this is why, like, even though they're super easy reactions and they make pretty colors, this is why we don't give them to undergrads. Because I'd be like, don't dry that out. And you'd be like, so I should get a hair dryer and just dry this out all the way? No, don't do that. Don't use a metal spatula. So I should just throw a bunch of pennies in with this? Dear God, where did you get pennies? Who has change? Right? It'd just be too dangerous. Right? So what these are really good for, though, are things called Sandemeyer reactions. So you've made them, you followed all the rules, they have not blown up, you have all your fingers. So you can do a Sandemeyer reaction. Congratulations. So in the Sandmeyer reaction, we're able to take off the diazonium and replace it with a group from a copper 1 salt. So you have your diazonium, then you add like copper 1 halide, usually like chlorine, bromine iodide, and you're going to replace the diazonium and put a halide on in its place. So again, what's nice is you know where, sure. Also, is this like the room that air conditioning forgot? Because it just feels miserable in here. Okay, I'm not the only one. Good. Okay, cool. Sure. All right. Right, you don't have to worry about like, again, directing groups or anything. You're like, I know where my diazonium is, so I know that that's where I'm going to put my halide. Right, so you can do this with like copper halides, you can do the same kind of reaction with copper cyanide. All right, now the early classes I hadn't told you guys about when I almost got gassed by an undergrad. So I think I have them. My first project in grad school, I used tons of copper cyanide, and I, you know, kind of got to like the smell, which is probably not a good thing to like the smell of, right? So then 2 years after I did that project, I'm in another lab and I have an undergrad working like the hood across from me. And I was like, what's that smell? I know that smell. I like that smell. What is that? And then someone walks by and goes like, your lab smells like cyanide. And I was like, oh, you're right. It does smell like cyanide. Okay, let's figure out why. So I was like, hey, undergrad, what you doing? And she had taken sodium cyanide and then added a bunch of HCl to it, which makes a hydrogen cyanide. And hydrogen cyanide makes you dead. Hydrogen cyanide smells like almonds, and eventually it binds to all the receptors in your nose and you stop smelling, and then you die. You're like, that smells like almonds. Oh, cookies. Why can't I smell anything? And you die. I was like, so how much did you use? And she's like, two equivalents? I'm like, no. Is there like a gram in there or are there 100? I was like, let's close the doors, close the hood, and let's leave the lab. We'll just come back later. It's a good time for lunch. Let's go. So yeah, that's why I don't trust undergrads. One tried to gas me. One of your kind tried to kill me once before. Just like never again. Never let my guard down. Right. Yeah, I also tried to kill myself once. I had a flask in my head. I was like, huh, what's all this dried up nasty stuff? Let me just pour some bubbles. And I was like, back in the hood. Oops, my bad. Someone asked me, so how much hydrogen cyanide does it take to like kill you? I was like, less than I've breathed? Like, I don't know. like I've not hit that threshold, thankfully. All right. So we can do it with copper halides, copper cyanide. We can also make phenols. So in all these cases, I'm using copper 1 salts, right? So here I've got 2 coppers and an oxygen, right? Oxygen is -2. Each copper is +1, right? For copper chloride, chloride's -1, copper is +1. This doesn't work with copper 2. It only works with copper 1. So it has to be copper in the +1 oxidation state. Now, if for some reason you were like, you know what? I don't want this nitrogen on my molecule anymore. I just want it to be a hydrogen. We can do that too. So if you just add phosphoric acid to it, you'll remove the diazonium entirely, and you will put a hydrogen in its place. So again, we're not worried about any other functional groups, directing group abilities, nothing like that, right? You know that wherever your diazonium is, that is where whatever you're adding is going to end up. right? So that's nice, right? You never have to worry about directing group stuff. It's just wherever your diazonium is, you know you're adding your thing. I want to point out this is the only way you know how to add a CN to a benzene ring, right? Is diazonium salt with copper cyanide. So if you ever see a cyanide on a product, you should think, oh, that had to be a diazonium salt at some point for me to get this. Reasonable? So what do you know? And you're not allowed to say nothing. You know stuff, or my life is a waste. What's the diazonium salt? Which letter? You're right, there is a diazonium salt. So where the nitrile is had to be a diazonium salt at some point in its life. I'm going to assume that is E was a diazonium salt. Right? And we just went over how you turn the diazonium salt into the nitrile, right? You add copper cyanide. You don't sniff it, even though it smells so good. Don't do it. Right? So how do we get from a benzene to an aniline? Or how do we get from the aniline to the diazonium salt? That's something we did today, so you should all know it. It's like fresh in your heads. So we can add the sodium nitrite and H2SO4, that works. So now I've got to turn my benzene into an aniline. How do we do that? So there's no way to add NH2 directly. We have to make it another functional group first. So what's a functional group that we know that we can put on a benzene ring that has a nitrogen in it? NO2. Yeah, so this B is a nitro group. Right, so B is a nitro. How do we add a nitro group? HNO3 and H2SO4. How do we turn a nitro group into an amine, into an NH2? There are two like big categories of how to do this, but one of them has three different options. So there's four things. There are four things you could say. It is a reduction, but like you can't just throw reduction over the arrow and be like, yeah, we good. You gotta tell me how you do the reduction. So palladium on carbon, yes. Like the worst games of Hangman ever. Right. So right, if you see a nitrile, you have to think it was a diazonium salt. You gotta remember that to get to the diazonium salt, it had to come from an aniline, and then that aniline, if you just have a benzene, had to come from a nitro group. So there's one more kind of like broad category of reaction I want to talk about, and that's the reactions at benzylic carbons. So the carbon bonded to the aromatic ring is the benzylic carbon. Right. So you get different kinds of reactivity than you would expect being at the benzylic carbon because you're beside an aromatic ring. And when you react at the benzylic carbon, there's a chance to get resonance stabilization and a lot of like kind of helpful stabilization and helpful interactions that allow reactions to occur. So I want to look at two types of reactions. The first is going to be halogenation. So this is the same kind of radical halogenation we did in organic 1. Right? If you have a benzene ring and you treat it with Br2 and light, you're going to preferentially make the benzylic bromide. You're going to put the bromine on the benzylic carbon. If you remember, kind of the whole point when you do a radical bromination with just Br2, right, is the bromine radical is trying to make the most stable carbon radical it can. And right, it has two choices really. It can make this radical or it can make this radical. Both of those radicals are secondary. But the black one is also benzylic. So you could draw resonance structures where that radical moves through the benzene ring. Thus, that radical ends up being more stable than just a secondary radical that's just stuck on that carbon. So your bromine is going to preferentially try to make the secondary benzylic radical as opposed to just a secondary radical. Similarly, there's another reagent, right, that kind of acts the same way, and that is NBS. And it's going to do the same thing. It's going to put the bromine at the benzylic position. So NBS is N-bromosuccinimide. And so it has this weak has this weak N-bromine bond that when you shine light on it, it breaks into radicals. And those radicals then go do the radical reaction. Now, kind of like when we did diene reactions, we had like made a carbocation, we said always make the alylic carbocation. Here, we're going to pretty much lean on always make the benzylic radical. So always react with the benzylic carbon, because that's just going to be more stable. Right, I have this, or I have this. This is tertiary, this is secondary and benzylic. So the extra stabilization you get from resonance is going to make you want to make the secondary benzylic radical more than the tertiary, right? Because that resonance is kind of making up the difference between secondary and tertiary, and then some. So we're going to put our bromine at the benzylic position.
So the question was, what is the dot that I keep drawing? What does it mean?
The dot is a radical. So, you've got a plus is an empty orbital, right? So carbocation plus empty orbital. A minus is a full orbital with 2 electrons in it. Well, the dot is an orbital that only has 1 electron in it. So it's a half-filled half-filled orbital. So they're more reactive than kind of anions and to some degree cations, because electrons really want to be paired. So when you break them up and they're not paired anymore, they just are desperate to grab an electron or some way to end up with an electron pair in that orbital again. So the dot is the radical, is that unpaired electron. Sure. And then, right, this also works on primary carbons, right? Because this is right, you make a primary benzylic radical, and that radical is significantly more stable than a primary radical would be. So again, the resonance is letting us do that. So even though the benzylic position is more stable, chlorine still doesn't care, right? So just like when we did this before, if you'd use chlorine, you end up making a mixture of products. Because chlorine is going to react with whatever hydrogen it bumps into first. It doesn't care about how stable the radical is that it's generating. It's just mad that it has an unpaired electron on it, and it wants to grab a hydrogen to pair up that electron, and it doesn't matter. Whatever hydrogen it bumps into first, you get a chlorine there. So still, even with the benzylic position, chlorines are going to just make a mess. So just like last semester, if I'm going to give you a radical halogenation, it's going to be with a bromine or with MBS, because you can predict where those are going to go. Right? They're always going to make the most stable radical. Right? Now the last benzylic reaction we have is oxidation. Right? So So KMNO4 turns benzylic carbons that have at least one hydrogen on them into carboxylic acids. So go to KMNO4, and that's going to turn that methyl group into a carboxylic acid. Now, it doesn't matter how many carbons are on the benzylic carbon or how long of a chain is attached to it. As long as there's at least one hydrogen on the benzylic carbon to kind of get the reaction started, to let KMNO4 start reacting, you're always going to end up making benzoic acid. So I come over here and I have, my propyl group here. So you have like this propyl group and KMNO4. You're going to chew off all the carbons and just end up with benzoic acid. So when we do these reactions, we don't really care about the other carbons, that carbon chain. So that just ends up being another carboxylic acid that we just kind of ignore and we don't care about. We usually only care about the aromatic side of these reactions. Right, so that's where the rest of it goes. But as long as you have one hydrogen on your benzylic carbon, you're going to make a carboxylic acid. Now, as soon as you don't have a hydrogen there, right, so let's say this is tert-butyl, you get no reaction, right? The KMNO4 is reacting with that hydrogen and pulling it off and starting the reaction from there. As soon as you get to a position that you don't have a hydrogen, there's no place for the KMNO4 to start the reaction to then take off your carbon chain. Right, so I've got, two hydrogens, one hydrogen, and then I have zero. Right, so you need at least one. Right, so in the first example, both carbons have a hydrogen on them. So they're both going to be oxidized to carboxylic acid. So I'm going to make the diacid here. This next one, we have hydrogens on the ethyl group, but none on the tert-butyl. So I'm only able to oxidize one of the two sides. So I'm just going to make one carboxylic acid here. So far, so good. So that is the end of all of your aromatic reactions. So what I'm going to do on Wednesday is we're going to go through some synthesis examples. So on Moodle right now, there's a sheet of a bunch of different syntheses. And I'm going to go work through that on Wednesday. So we're going to go through all these different synthesis examples and get everyone some practice on that. And then that'll kind of finish up aromatic stuff.